Hello, my name is Maanav, and today I'll be presenting about my agent-based model for rabies intervention. So, rabies is a fatal disease that causes brain inflammation, and it's typically spread through different animals such as dogs, causing the symptoms shown on the screen here. Rabies causes 59,000 deaths each year according to World Health Organization, and 36% of those deaths actually occur in India. If you look at the rabies cases in India, this is only worsening with 2.6 million cases in 2022 and 3.3 million cases in 2023, indicating that this is a worsening problem. Literature reviews tell us that the accuracy of traditional epidemiological models are limited because they assume homogeneous mixing. They fail to account for vector movement, which impedes their accuracy. And this is the gap of the project that we're actually filling. We're trying to account for dog mobility here in our model. The scope of our project will be limited to the Indian state of Kerala and the Indian city of Delhi due to data availability. Now, before we chose agent-based models, we actually looked at other alternatives. We looked at neural networks, but we didn't choose them because they are black box, meaning that they're hard to interpret or adjust. We looked at compartmental SEIR models, but they assume homogeneous mixing. And if you look at the hybrid between the two, that requires dense data sets. We came in our research we came across other spatial ABMs like EMOD and GleamVis, which were historically successful in simulating different diseases such as smallpox, and we decided to extend that to rabies. Now, for our model, we create a Mesa Python grid, which is basically a uniform square, and then we randomly populate the agents across this grid. Each agent can either be susceptible, exposed, infected, recovered, or diseased. Now, the next part of this model is actually inputting the values. So what we did is we found the corresponding values of dogs, humans, initial infected dogs, so on for the state of Kerala and then the city of Delhi. So once the parameters are inputted as shown before, the model goes through this cycle shown on the left side of the screen. So based upon the agents go through its random movement, and based upon whether an agent is close to another agent, it transitions to certain phases, and so on. Right, so on the right side of the screen, you can see all the math, and all I need you to understand about the math is that it's probability based, and these probabilities are computed based upon the original parameters which you input. Now, my model predicted 47 deaths versus actual 48 in Delhi, which is a 2.1% error, and 21 versus 22, which is a 4.5% error. To the right, we also see that there is the infection density per area on the graph, a distribution of it, not verified against real world data. Now, what I'm about to show you an example of a policy insight which we could actually extrapolate from the model. You can see a dog SEIRD graph, and we can see that the exposed number of dogs stays relatively constant at the beginning, and then the number of dead dogs rapidly increases, which means that there's barely any dog-to-dog transmission. But in the human SEIRD disease progression graphs, the number of exposed and number of dead increases with respect to time. And this tells us that dog to human is a primary channel for transmission. The human SEIRD graph is not shown on the screen. Now, from that, we can get a policy insight that dog to human is a dominant transmission pathway, so we should prioritize human PEP vaccination to address that pathway. The model also has been verified using real world data, and the main thing is that the model's framework is applicable to other diseases beyond rabies with animal vectors. The limitation of this model is that we're assuming a closed population. We're not assuming that seasonal effects will be at play and then the population will fluctuate. The model actually uses a square grid, which is not the real shape and the geography of the different regions. And we have a risk of overlaps on point estimates because we're only looking at the number of rabies deaths to validate the model here. Now, the model, if we're looking to pilot the tool in collaboration with the GARC and the Indian State Health Ministries, specifically integrating India's Integrated Disease Surveillance Program, and we're looking to incorporate multilingual training resources to make it really accessible to use, and then talk about it at One Health workshops, right? And if this model is used in 80% of regions in India where rabies is prevalent, then our BOTEC estimates that 6,000 to 18,000 lives will be saved per year, and 11.52 billion US dollars in economic value will also be saved for India. Thank you for watching. Just to give a little tour of the actual outputs of the model itself, researchers can look through each day and look at the amount of susceptible, exposed, infectious, recovered, or dead, so that they can come up with valuable insights. They have epidemiological curves, spatial distribution, and data reports to actually look at to guide their conclusions. Thank you, and I hope you enjoyed this presentation on our ABM.